series of the geometry of SL2Z, and today we're going to be talking about complex elliptic curves, and we want to express how the region, the space we defined before is the quotient of the upper half plane by the action of SL2Z, how this is the moduli space for complex elliptic curves. In other words, it parameterizes all complex elliptic curves. So we're going to break down exactly what that means in today's video. So a lot of people, when they first come across elliptic curves, they're told that there's something in terms which are described as y squared equal to x cubed plus ax plus b. And oftentimes we're interested in when these coefficients belong to the rational numbers, and we want to find rational solutions to these such equations. But, you know, we can also, of course, look at these over, say, the real numbers or the complex numbers. Now, if we plot these out in the real plane, which is perhaps the nicest way to get some sort of visualization of this cubic equation, we typically get two different shapes. One that looks like this, or we will sometimes get a shape that looks like this, where there's a blob that's been disconnected. So these are the two types of two ways that we can view an elliptic curve in the real plane, depending on what the coefficients a and b are. And so what's all the hoopla about complex elliptic curves, or elliptic curves in general? What makes these so special? Why are these important, deep parts of number theory and geometry? Well, this isn't a full answer to the question, but one thing that's really nice about such curves is that they have what's called a group law. In other words, we can take points on this curve and define some sort of operation, which we call addition, on these curves, and it satisfies the axioms of a group. So the way in which we do that is we consider a point, say two arbitrary points P and Q, lying on our curve. Then by Bézou's theorem, in projective geometry. So I'm saying the word projective. It's not clear that this is projective yet, but we'll get to that in a moment. If we take the straight line through P and Q, this has to intersect our elliptic curve in a third point. And then instead of taking that point, we're going to reflect across the x-axis. And that's, we're going to call this third point R. And so when this happens, we define the group law P plus Q on this curve to be the point R. And now this ends up satisfying all of the axioms of a group law. Associativity, as is oftentimes the case, is the most difficult to check. But we also need a identity element. It's not really clear from what I've drawn what the identity element should be. You might think, well, this one sort of extremal point at the tip of the curve, maybe that's the identity element, because it's the only obvious point that stands out alone without any symmetry. However, what we actually do, as I just mentioned the word projective, we toss in a point at infinity. Now, I've drawn this up above the y-axis, but really we're sort of thinking about it as being everywhere far away from the origin. Or more specifically, any point at all that's far away from the origin is close to the point at infinity. And so it's the point at infinity that's going to serve as the identity for this group law. Okay, so this cubic equation is nice, and this group law is nice, but I haven't been very general with you. There's a more general definition, which I'm going to mention in a second, and well, actually this isn't even the most general definition of an elliptic curve. But more generally, we can say that an elliptic curve over an arbitrary field K. This is, and I'll explain these terms in a moment, this is a smooth, one-dimensional, projective variety over the dictated field with a point, a distinguished point of the curve of genus 1. So let's break down what all this means. So the condition that this be smooth, well, this is just a sort of niceness condition. Basically, it means that a curve doesn't have any weird sort of cusps like this, where, you know, the tangent line is ill-defined. There's no sharp points at all. One-dimensional is, of course, one-dimensional, so we're talking about curves. This should make sense. Projective, so we've already sort of seen this in the plot of our real curve, where I mentioned that we toss in this point at infinity in order to have our group law have an identity, which essentially turns this into a projective space. Variety, now don't at me, algebraic geometers, but basically this just means anything that can be described, anything that can be carved out by some sort of polynomial equation. Over K, of course, this just refers to the base fields that we're working with. The distinguished point that we're dealing with is simply what the identity point is for this curve. And then of genus 1, this is the thing that's a little bit different. So you might have seen, if you've read some pop math or, taken some topology, you might have heard that the genus of a surface is the number of holes it has in it. So this triple donut has genus equal to 3, for example. Now, this is sort of a weird thing to think about because this definition works for any field K. So this could even be for, say, some finite field of order p to the n. And in which case, the topological notion of genus doesn't really make a whole lot of sense. The full definition, the real definition, if you want, comes from something called the Riemann-Roch theorem. And the Riemann-Roch theorem is actually what we use to get from this fancy, complicated definition, and it actually implies that we can always write this as some sort of cubic curve, with the caveat that the characteristic of the field we're working with is not equal to 2 or 3. Now, the only thing that goes wrong in this case is just, so we still get a cubic curve. It just might be more complicated than the form that it's written here. So Riemann-Roch theorem implies this. Richard Borcherd has some really nice videos he just put up about the Riemann-Roch theorem, including the relation to elliptic curves, complex elliptic curves specifically, and I'll post those in the description below. So really, a complex elliptic curve does turn out to just be a torus. Now, you might be scratching your head at this point because I just told you that this is supposed to be something that's one-dimensional, and over here I've drawn a torus, which is very clearly two-dimensional. So what's going on here? Well, the trick to this is that the complex numbers themselves, topologically speaking, this is just R2, right? We have two copies of the real numbers glued together. So if you're looking at things from the perspective of the real numbers, yes, this certainly looks like something that's two-dimensional as a manifold. But from the perspective of the complex numbers, it's only one-dimensional because for the complex numbers, we just have one copy of the complex numbers, right? And over here we have two copies of the real numbers. So even though this, we like to draw this as a surface, from the perspective of the complex numbers, this is still something which is one-dimensional. I realize that might be a little bit confusing, and hopefully this next section will give another layer of believability to this fact. So let's consider ourselves to be working in the complex plane. I want you to pick two complex numbers, any two complex numbers, which are, we'll call them omega 1 and omega 2, where omega 1 is not a real scalar multiple of omega 2, which is to say that these two complex numbers are real linearly independent. And suppose that I were to translate this pair of vectors over by integers in every direction. So I've picked my vectors omega 1 and omega 2, and I'm simply just, I'm considering the vector from the origin to omega 1 and omega 2, and I'm just translating these two vectors, and I'm continuing to do this until I've completely tiled the complex plane by these parallelograms. So really, I've tiled all the complex plane by just a bunch of copies of this sort of fundamental parallelogram. In other words, if we consider all the points, the intersections of all of these, we get what's called a lattice. And this is really just all integer combinations of omega 1 and omega 2. Now, you may have seen before, one construction of building tori is you take a parallelogram, and with the appropriate orientation of the edges, say we identify first the top edge and the bottom edge, so we end up getting this long tubular shape. And then we identify the two ends so that the arrows match up, and this ultimately gives us a torus. So if we were to take our complex numbers and we were to pick some lattice and mod out by the lattice, really we're identifying each copy of these integer translates, which really means that we're taking the edges of this fundamental parallelogram and identifying them. Well, this gives us a torus. And in fact, all complex tori arise in this way. In other words, complex elliptic curves are really just complex tori, as we've seen above. And so to every complex elliptic curve, we can associate some lattice to that curve. One thing that's nice about this is it makes the group law a little bit more obvious, because the complex numbers is already a group, and one can check, so we're thinking of this as a group under addition, and one can check that the lattice is a subgroup of the complex numbers under addition. And since C is abelian, the lattice must be a normal subgroup, and so the quotient of C by lambda is also a group. And so this makes it a little bit more obvious, where we just take the standard quotient group rule. This is also another reason why it's one-dimensional from the complex numbers, right? The complex numbers themselves, we have this one-dimensional, this one copy of the complex numbers, and we're simply modding out by some lattice. So as far as the complex numbers are concerned, this is all one-dimensional. Whenever we talk about objects, of course, the very next thing we want to do is talk about morphisms between those objects, because that really tells us what the structure is that we care about. I'm not going to get into why this is the case here necessarily, but for an elliptic curve, it turns out that considering what a morphism or isomorphism of elliptic curves should be, if we have an elliptic curve associated to the lattice lambda, it turns out that the elliptic curve associated to lambda multiplied by some non-zero complex number will give the same elliptic curve. So these two lattices correspond to the same complex elliptic curve. This means that if I were to have some lattice, which is the span of two complex numbers, omega 1 and omega 2, as far as the elliptic curves are concerned, this is equivalent to the lattice by multiplying by the inverse of omega 2, which we have would be the integer span of omega 1 over omega 2 and 1. And we'll often write this, writing z as a shorthand for omega 1 over omega 2, we denote this lattice lambda sub z. So now, to every complex elliptic curve, we've really turned this into something that just depends on one parameter. So to every complex elliptic curve, there exists some lattice lambda z corresponding to it, and vice versa. Furthermore, if it was the case that the imaginary part of omega 1 over omega 2 were negative, well, then it would have to be the case that the imaginary part of omega 1 over minus omega 2 were positive. And if I am to look at the lattice span, which is the integer span of omega 1 and omega 2, and I replace omega 2 with minus omega 2, so if I had some integer combination with integers a and b of omega 1 and omega 2 belonging to the lattice lambda, I can rewrite this as a omega 1 plus minus b minus omega 2. And now this is still in the lattice lambda, but it's written in terms of minus omega 2, and vice versa. If I started with something like this, I could rewrite it in this form. So really, the lattice, by swapping omega 2 with minus omega 2, I get the same lattice on the nose, not even just up to equivalence of associated elliptic curves. I get precisely the exact same lattice. So what that means is we can always choose representatives for our lattice such that the imaginary part is strictly greater than 0. In other words, to every complex elliptic curve, we can associate a lattice, lambda z, where z lies in the complex upper half plane. This also raises another question, though. We were able to find some transformation that we could do to one of the vectors, which left the lattice unchanged. Another way to phrase this is, what sort of integer bases can we possibly have for a lattice? What operations can we do to omega 1 and omega 2 and get the exact same lattice on the nose? So let's suppose I have an omegas lambda spanned by omega 1 and omega 2, and that this is equal not just in the sense of elliptic curve equality, but in the sense of being directly the same lattice, containing all of the exact same vectors. And this is spanned by some two different elements, omega 1 prime and omega 2 prime. Well, if this were the case, then omega 1 and omega 2, these must belong to capital lambda prime. This means that omega 1 is equal to some integer combination of omega 1 prime and omega 2 prime. I'll call those integers a and b. And I can say a similar thing for omega 2, just using integers c and d. Now, a more compact way to write this would be to say that the matrix a, b, c, d, multiplying the column vector omega 1 prime, omega 2 prime, results in the column vector omega 1 and omega 2. I'll call this matrix gamma. Now, using this exact same argument, but now just considering that this also means omega 1 prime and omega 2 prime must belong to the lattice lambda, that means that there exists some integer matrix beta when I multiply omega 1 and omega 2 as a column vector. I should get omega 1 prime and omega 2 prime. But this means that gamma and beta are inverse matrices to each other. So gamma multiplied by beta is equal to the identity matrix. And if I'm to take the determinant of both sides of these, I get that, well, the determinant of the identity matrix is always equal to 1. And I have that this is equal by the product property of determinants. This is the product of the determinants of gamma and beta. But gamma and beta, these are integer matrices. So their determinants must be integers, and the only way that we can have a product of integers equaling 1 is if both of these are just plus or minus 1. From linear algebra, a matrix is called orientation preserving if and only if its determinant is strictly positive. In other words, and this word orientation corresponds to the literal orientation of these two vectors, omega 1 and omega 2. And so we're keeping the orientation the same, which turns out to be equivalent to keeping the imaginary part strictly positive. Because again, remember, we only need to restrict our attention to when z is in the complex upper half plane. So we really only care about those matrices which are preserving the positivity of the imaginary part of the quotient of the spanning vectors. So therefore, we conclude that the matrices gamma and beta have determinant positive 1. But if gamma and beta are integer matrices and they have determinant positive 1, this just means that they are elements of SL2Z. So in other words, if I have two lattices, lambda and lambda prime, and I know that they're equal on the nose, then their bases elements only differ by a transformation of SL2Z. Conversely, if I had a matrix gamma, and I were to multiply omega 1, the column vector omega 1 prime and omega 2 prime, and it yielded some elements omega 1 and omega 2, where so gamma belongs to SL2Z. Well, this is just saying that omega 1 and omega 2 are integer linear combinations of omega 1 prime and omega 2 prime, which means that omega 1 and omega 2 belong to the lattice lambda prime. And if I were to take gamma inverse and apply this to omega 1 and omega 2, of course this gives me the column vector omega 1 prime and omega 2 prime. And thus I know that omega 1 prime and omega 2 prime, those belong to the lattice capital lambda. And since the bases elements belong to each other, I know that these lattices are equal on the nose. In other words, two lattices are equal on the nose if and only if they differ by some element of SL2Z. To package this up in a slightly different manner, so let's now consider the action of a matrix gamma on a pair of real linearly independent complex numbers, omega 1 and omega 2, and we'll call omega 1 prime and omega 2 prime the image vector of that. And I have my lattice lambda, which is the integer span of omega 1 and omega 2. Now, as far as complex elliptic curves are concerned, this is, in the sense of complex elliptic curves, equivalent to the lattice lambda sub z, which is the integer span of just z and 1, where z is the quotient omega 1 over omega 2. Now, what were to happen if I took this lattice lambda sub z and I were to look at the lattice lambda sub gamma z? Well, writing out our action for Mobius transformations, this would be the integer span of az plus b over cz plus d and 1. Now again, as far as complex elliptic curves are concerned, I can multiply by scalars. So I could multiply this by cz plus d, and this will be equivalent to the lattice spanned by az plus b and cz plus d. But z is omega 1 over omega 2. So again, as far as the associated elliptic curve is concerned, I can multiply this lattice by omega 2 to get the equivalent lattice, which is the integer span of a omega 1 plus b omega 2 and c omega 1 plus d omega 2. But we said that this is just that a omega 1 plus b omega 2, this is omega 1 prime. So this is the lattice z omega 1 prime and omega 2 prime. But this lattice, since omega 1 prime and omega 2 prime is just a change of basis by SL2Z, this is equal on the nose to the lattice spanned by omega 1 and omega 2. And finally, once more, up to equivalence of complex elliptic curves. By multiplying by lambda 2 inverse, this is just the same thing as the lattice lambda sub z. What we found then is that the complex elliptic curve associated to the lattice lambda sub z is the same complex elliptic curve associated to the lattice lambda sub gamma z. So looking at this argument, and the fact that two lattices are exactly the same if and only if they differ by the action of SL2Z, we're left to conclude that the complex elliptic curves associated to the lattice, some lattice lambda z and some lattice lambda sub w, these are the same if and only if z is equal to gamma w for some gamma in SL2Z. And remember that z and w, these only belong to the complex upper half plane. Therefore, the complex upper half plane modulo the action of SL2Z, which we write on the left for reasons that become apparent later on in study of modular forms. This parameterizes complex elliptic curves. In other words, for each point in the space, which is the upper half plane modulo SL2Z, there is a unique complex elliptic curve associated to that point, and all such complex elliptic curves arise from these points. So we say that this geometric space is the moduli space for complex elliptic curves. That is the fundamental region that we drew before. Every complex elliptic curve is parametrized by the points of this fundamental region. And so this is why, one of the reasons why this is such an important space. So that covers everything for this video. In the next video, we'll explore a bit of the geometry a little bit further and see how this leads, in some sense, to the definition of a weakly modular form and modular forms in general. As always, I really appreciate your questions, comments, and concerns if you want to drop them in the comment section below, and thanks for watching.